Now that the architecture is in place, I have uploaded the bare minimum project to GitHub. Let's clone it and walk through how the build system, testing setup and design choices come together. We start by cloning the repository in Ubuntu and opening in VS Code. Once inside the project, the first file worth looking at is the build and test script. This script automates the full cycle, cleaning the build directory, configuring CMake, building with Ninja, running test and generating coverage report. This is intentionally minimal, just enough to automate the workflow while keeping everything transparent. We will improve it as the project grows. I switched the compiler to CLang because it gives clean human readable diagnostics, first class sanitizers and excellent code coverage tooling. ASAN or address sanitizer helps us to catch memory issues early, like buffer overflows, use after free, invalid access, and so on. And we can catch it long before they become runtime bugs on hardware. So let's go ahead and install these toolchain. Now we are ready to run the script and generate code coverage. But before building our project, let's have a look on our source. We have source directory and test directory separately for source files and testing files. The project is intentionally structured to make unit testing natural, not painful. Dependency injection allows us to inject mock, isolate modules, test behavior without hardware, and avoid global state. This is the opposite of singleton, which is notoriously hard to test and often considered an anti-pattern. Interfaces like iUART and iGPS source are abstract interfaces. They are not the implementation, and this lets us use real UART or mocked UART at any point of time without touching the dependent code. The UART implementation is selected at runtime, and this allows us to test the entire GPS pipeline using mock UART. The GPS pipeline is a clean chain: GPS UART reader, GPS parser, and Neo4m GPS source. Each stage consumes input and produces output. This structure is naturally testable because each stage has clear expectations. Let's look at one concrete example: read sentence method of GPS UART reader. This function reads a single NME line from UART. In the test, we inject a mock UART into the header, and we can write our test case independent of our hardware UART. If I open the test case for UART reader class, we can clearly see that we can mock the UART interface and create the UART reader object out of it. And here we can test the read sentence function thoroughly. This is the power of dependency injection plus interfaces. Now we run the test script. We can ignore this warning for now, but we can see all our test cases are green. You will see that all test executes, followed by coverage generation. Opening the report shows which lines are covered, which branches are missed, and whether improvements are needed. This gives us a clear roadmap for improving the code quality. With this bare minimum project working clean build, sanitizer, coverage and modular design, we are ready for the next step, which is compiling the project for the real hardware. Thanks to the abstractions that we built, only the hardware specific layers need to be changed. Everything else stays the same. And that's the power of good architecture.